Hello, in this video we study how to find the area of some surface over some region. Look at this very simple picture. Suppose that you have some square right here on the xy plane, okay? And you have some surface z equal to fx and y. I want to find the area of the surface over this square. So, corresponding to vertices of this square, I have 4 points on the surface, right here. Okay, it's very difficult to find the area directly. So I would like to approximate. I will pick arbitrary point xy, right? I call xi, yi in the square. And then for this point, I have corresponding value zi, which is zi equal to fxi, yi. That is a point on the surface. And now, I want to approximate the area of the surface over the square by the area of some parallelogram. How? At this point, I will consider derivatives in the direction of x and y axis. Make sense? So we learned that topic already. I pick some, directional derivatives in here, and then for these directional derivatives, I will have some tangent plane. Make sense? Okay. So we have some tangent plane in here, and we can find 4 points which are corresponding to those vertices of the square on this tangent plane. Let's say this one, and this one. Okay, so then I can approximate the area of the surface by the area of this parallelogram. Okay, so that is the whole idea. Maybe the picture is not great, but look at this. If we consider one-dimensional case, right? One-dimensional case. I want to find the arc length of this guy. We learn this problem in calculus too, right? So I may approximate the arc length using the distance between these 2 endpoints. Make sense? Or I can pick an arbitrary point on the curve, and I can pick, the tangent line to the curve, and I choose 2 points right here, which is corresponding to 2 values a and b in here in the x-axis. Make sense? And I already have another approximation of the arc length. So that is the distance between these 2 points. That is the one-dimensional case, right? If you have another dimensional case, so suppose that you have the x-axis right here, right? So if you have another axis like the y-axis in here, so which is perpendicular to the x, probably at this point you also can consider some, straight line, right? Which is tangent to that. Or if we consider the function of 2 variables, that is nothing but the directional derivatives. Make sense? So, if you generalize this case, the case of arc length to the case of surface area, so you would have the following picture. The first one, the formula of the arc length looks like equal to integral from a to b. Here I have 1 plus derivative, right? Square and dx. That is the one-dimensional case. If I have 2-dimensional case, I would have the following formula. Surface area equal to double integral over the region R, right? And here we have partial derivatives, because we already consider, derivatives in the x and the y direction. So I'll have 1 in here plus fx squared plus fy squared, and then dA. Makes sense? That is very naive generalization from the arc length problem to the surface area. Okay. Of course, in order to prove this formula, we need to involve cross product. We need to find, the area of each parallelogram right here. But that is a long way, and you can see detail in the textbook. I just try to explain how to generalize from the arc length formula to the surface area formula. Means from the case of function of one variable to the case of function of two variables. Okay, so you have to copy this formula in your formula sheet. And let's consider the following example. They ask us to find the surface area of the portion of the plane z equal to 2 minus x minus y that lies above the circle x squared plus y squared less than or equal to 1 in the first quadrant. Okay, so they are talking about circle x squared plus y squared less than or equal to 1, and in the first quadrant. Basically, what is that? That is x squared plus y squared less than or equal to 1 and xy greater than or equal to 0. Make sense? All right, now let's draw that out, and then we'll see the picture. So here is my x, y, and z. I have to plot the plane, right? Z equal to 2 minus x minus y. So if x and y are 0, z is 2, right? 2 is right here. If x and y are 0, x is 2. Okay, and if x and z are 0, y equal to 2. So that is my plane. Z equal to 2 minus x minus y. And on the xy plane, we have circle radius equal to 1 and center at the origin. So we consider only the first quadrant. I would have the following one. Here's 1, here's 1, and that is my region in here. And we consider the surface, the portion on the plane, right? Which is, here we should have some intersection. Make sense? So this is our solid region right here. I hope that you can imagine the picture. And they ask us to find the area of this part. Okay, let's apply the formula. We have the area is equal to double integral on the region R. Here we have 1 plus z partial derivative with respect to the x squared plus z partial derivative with respect to the y squared, and then dA, right? So that means we have to find partial derivatives in here. But that is pretty easy because, the function is linear. So I have z with respect to the x is -1. Z with respect to the y is also -1. Basically, if we plug this into the area formula, we have R 1 plus 1 plus 1 and dA, right? The constant can be taken out. We have square root of 3 R right here and dA. Okay, so what is this? This is nothing but the area of the region R, which is 1/4 of the area of the circle, right? So the area of the circle is pi times 1 square. Here we have square root of 3, and since that is just 1/4, we have to divide by 4, and the answer is square root of 3 over 4 times pi. Luckily, in this situation, we don't have to rewrite our integral in terms of iterated integral. I would like to mention one more thing. Our surface is above the xy plane. That's why we can use double integral to find area. So I hope you still remember the picture when we studied area problem in calculus 1. Like if you have some function f like this, right? And you want to find the area of this region and this region. So you have to break your definite integral into two integrals, right? Because if you just take integral from a to b f of x dx, the answer is not correct because you have negative area right here. Makes sense? So we have to be careful, you know, in its surface area problem too. We have to make sure that, you know, the surface is above or under the xy plane. Makes sense? But most of the case, we will have, you know, surface that lies above the xy plane. So I just mentioned that in case if we need to do, if we need to break the integrals into some integrals. Okay. In the following example, we need to find the area of the portion of the surface fxy 1 minus x squared plus y that lies above the triangular region with vertices at 1, 0, 0, 0, negative 1, 0, and 0, 1, 0. So they already give us the region, right? We need to plot that. Okay. The picture looks like this. This is x, this is the y, this is the z. The first vertex is 1, 0, 0. Right here, 1, 0, 0. The second one is 0, negative 1, 0. So I have this one, 0, negative 1, and 0. And the next one is 0, 1, 0. Our region looks like this triangle. Okay. Now we need to plot the surface. So based on the equation, z equal to 1 minus x squared plus y. If x and y are 0, z is equal to 1. Okay. So if x is 0, y is negative 1. So the z 0 already. So that means this point is also on the surface. So luckily, and here, how about this point 1, 0, 0? When x and y, when x is 1, y equal to 0, z is also 0. That means this point is also a surface. Perfect. Now, how about this vertex? If I plug x equal to 0, y equal to 1 into z, so I get z equal to 1 plus 1 is 2, right? So 2 is right here. I have another point on surface right here. So basically, you know, these 3 points are on the same straight line, and this guy something like this. Okay, so I hope that you can imagine, right? And they ask us to find the area of the surface. So the surface look like this. This is our surface. Okay, and we need to find that. All right, let me put this. This is 0, 1, and 2. Okay, so again, we need to use the formula. The area is equal to double integral on R square root of 1 plus fx square plus fy square and then dA. So we need to find partial derivatives. Fx is equal to negative 2x and f with respect to the y equal to 1. Okay, and we plug these two functions into the area formula. We have the area is equal to double integral over r square root of 1 plus 4x squared plus 1 dA, and that is r square root of 2 plus 4x squared dA. So in this situation, we need to rewrite this in terms of iterated integral. Okay, so look at this region. If I plot the region separately on x or y plane, okay, I have the following picture. This is y, this is x. So y, the first point is right here, second point is right here, and here is the third point. So our region looks like this. You see that? So you know this point is corresponding to this guy. This point is corresponding to this guy, and this guy is corresponding to 1 0. Okay, it is 0. So the region R look like this. Now we already know how to do that, how to rewrite a double integral in terms of iterated, right? In this situation, how do you think? We integrate with respect to the x first and then y, or with respect to the y and then x? Probably the easiest way is we need to integrate with respect to the y first. That means we have to fix x first. Why? Because if we integrate with respect to the x first, right, that means we have to fix y. So if you want to fix y, you have to draw some horizontal line, right? And we need to consider two cases in here, because you know if the line is above the x-axis, so that intersect with the y-axis in here, and this straight line, one straight line at this point. If that straight line is under the x-axis, so you already need to consider the second case with another straight line. So I would think, yeah, maybe I have to fix x first, right? Because when I fix x, I just need to make one vertical line, right? And that vertical line will intersect with those straight lines at 2 points. I only need to find coordinate of these two guys, and I can find the interval of y. Makes sense? All right, so based on this observation, we will rewrite this in terms of 2 plus 4x squared, and since we fix x, I will integrate with respect to the y first and then with respect to the x. I need to find the integration limits in here. For x, I know that is from 0 to 1, right? We need to find y. That means we need to find this point and this point right here. But you know, it's easy to find the equation of this straight line because we know 2 points, 1, 0 and negative 1. So this is nothing but y equal to x minus 1, right? And this straight line is y equal to negative x plus 1. So based on this, we can see the interval of y in the integral would be from where? From x minus 1 to negative x plus 1. Makes sense? All right, so now we need to integrate that. For the inside integral, we integrate with respect to the y, and we have square root of 2 plus 2x 4x squared. That is constant, right? So basically, this is equal to integral from 0 to 1. In here, I have square root of 2 plus 4x squared y evaluated from x minus 1 to 1 minus x dx. And this is equal to 0 to 1. Here I have 2 plus 4x squared. I have 1 minus x minus 1 in here dx if we simplify this, we get 2 minus 2x, right? In here, I have 2 plus 4x squared integral from 0 to 1. Okay, and in this situation, we need to break the integral into two integrals. That is from 0 to 1, 2 times 2 plus 4x squared dx, and minus 2 times from 0 to 1 x 2 plus 4x squared dx. You know, the first integral has some specific form. This is integral of square root of a squared plus u squared. We need to check the integration tables. Okay, so this is equal to x square root of 2 plus 4x squared plus ln of 2x plus square root of 2 plus 4x squared. And for the second one, we can do substitution. We put u equal to 2 plus 4x squared right here. And when you find du, you get 8x dx, right? And you see, x dx is right here. Okay, so basically x dx is just du over 8. And then you rewrite your integral. You have the following one. The antiderivative of this looks like du square root of u and du over 8, right? I don't write integration limit because I want to plug, you know, numbers at the end. And we use the power rule, that is 1/8 u 3 over 2 over 3 over 2. Okay, so that is 1 over 16, because 2 with a will be simplified, and we get 12. In here I have 2 plus 4x squared to 3 over 2. Okay, so that is antiderivative. And together with 2 in here, we will have the following one, minus 1 over 6, because, you know, 2 with 12 will be cancelled out. Here I have 2 plus 4x squared to the power 3 over 2. Okay, and everything is evaluated from 0 to 1. From 0 to 1. The last step is just plug 0 and 1 into this function to find the integral, and that is I would say square root of 6 plus ln of 2 plus square root of 6 minus square root of 6 minus ln of square root of 2 plus 1/3 and square root of 2. Or this is approximately equal to 1.680. And that is the surface area of this. Okay, so, you know, I mentioned again, right? You know, we have to use integration tables all the time. For example, for such integral, yes, we know how to get this, right? But with the integration formulas, it's much easier and faster. And, you know, to get this form, it takes time, all right? So if you don't know that, there's no way to solve such a problem. To finish this section, let's solve one problem with polar coordinates. In this example, they ask us to find the surface area of the parabola z equal to 1 plus x squared plus y squared. It is right here. That lies above the unit circle. So here's the unit circle. This is -1, this is 1, this is 1, this is -1. Okay, so they ask us to find the area of this surface. Again, we need to apply the formula. The area is equal to double integral on R square root of 1 plus fx square fy square in here, and then dA. But you know, the region R in this case is the unit circle, and we know for such region it is much easier to use polar coordinate, right? But when you change the variables from rectangular to polar coordinate, don't forget we will have R in here, the factor R in here, okay? But let's describe unit circle using polar coordinate. That is R greater than or equal to 0 and less than or equal to 1. Actually, that is enough. And we know that theta will go from 0 to 2 pi. Okay, so I rewrite this, but first I need to find partial derivatives. Agree? Let's find partial derivatives. F with respect to the x, that is 2x. F with respect to the y, that is 2y. Okay, and so the area will be, you can integrate with respect to r first and then theta later. That is your choice. Okay, so we can write dr and d theta. Theta go from 0 to 2 pi, r from 0 to 1, and inside I will have square root of 1 plus 4x squared plus 4y squared. Let me keep x and y, and then I will plug, you know, r and theta into this formula. Here we have r dr d theta. Okay, so what is x? X is 2r cosine of theta, and y with together with 2 have 2r sine of theta. So if you just find 4x squared plus 4y squared, right, you will get 4r squared, because sine squared and cosine squared gives you 1. Okay, so basically I have integral from 0 to 2 pi, in here from 0 to 1, and then 1 plus 4r squared times r dr d theta. Agree? Yeah, we met this integral in the previous example. But one special thing in this double integral is, since the inside integral does not depend on theta, so we can write this as product of two integrals. So that is 0 to 2 pi and then d theta times integral from 0 to 1 r square root of 1 plus 4r squared dr, right? The first guy is just 2 pi. We all need to find the second guy. So for the second guy, I put u equal to 1 plus 4r squared. I have du is 8r dr. And from here we get r dr is du over 8, right? Let me find antiderivative of that function. So I have du, that is square root of u, du over 8, right? And that is 1/8 u 3 over 2 over 3 over 2, which is equal to u 3 over 2 over 12. So we substitute r back here. We get 1 plus 4r squared to 3 over 2 over 12. And this evaluated from 0 to 1. Alright, so now you just plug 0 and 1 into this function, and you get, at 1 you get 5 to 3 over 2 over 12, and at 0 you get 1 over 12. Overall, you compile this and this together, you multiply them, you get the answer. That is pi 5 square root of 5 minus 1 over 6, which is approximately equal to 5.33. So I think this topic is interesting enough, right? And at the beginning of the video, I mentioned the area formula is some kind of generalization of the arc length formula for function of one variable. Okay, and you know, sometimes we can use polar coordinate. It really depends on, again, the region of integration. Okay, so I hope that the video is clear enough, and if you have any questions, please feel free to let me know. Thank you.